Okay, we're looking at a service valve. Notice that we have the square head, which I referred to on the previous PowerPoint presentation. This is where the gauge is mounted here. This is a flare nut connection, of course, your copper line, which has a flare behind it. And this appears to be attached to a liquid line receiver. This is an example of a computer charge by CPS. They make good equipment. I'm not sure if this is a wireless version or not, but basically what you're going to do is determine how much refrigerant needs to be added to the system. You're going to utilize this keyboard here and enter the amount. And of course, in all probable cases, you'll probably use liquid. And then once you have entered the amount, then you just hit the go switch, and then basically it will remove that amount of refrigerant from the bottle into your refrigeration system once it reaches the set point that you have determined, whether it be like 3 pounds, 2 ounces as an example. It'll automatically shut down the flow of refrigerant, and it will tell you that the charge has been completed. And then your display is right down here. Here's an example utilizing a refrigerant scale. Notice we have a bottle of R22. In this position, this gentleman is charging refrigerant in the vapor state. The reason why I know this, the bottle is upright. If we were to invert the bottle or the valve stem is down, then he would be going with liquid only. Here we are zeroing out the scale so we can take and figure out, so we can add the refrigerant. This is a very important feature. Anytime we add refrigerant to a system utilizing the scale, we must zero out the scale so we get accurate readings. This is an example of bypassing the low pressure switch if we are going to liquid charge through the liquid line or king valve. In this particular case, the LP switch would normally shut the unit down. We're going to bypass the circuit here until the refrigerant has been added to the system. And at that point, we're going to remove this jumper and then restore the low pressure switch to its normal function. Here's an example of a PT chart. These are different refrigerants right here. For instance, these are you got 401, 402, 404, 407. Can't read this one very well. Oh, this is 407C, 409. And this would be an example of the blends. Notice that you have the dew point and you have the bubble point. Dew point for superheat, bubble point for subcooling. Please remember that. Dew point for superheat, bubble point for subcooling. And remember, these numbers fluctuate on blends because the chemical composition of the refrigerant is such that it's all over the map here when it comes to charging a system utilizing a blend. Please be aware of that. Okay, this is an example of a disposable refrigerant cylinder. Notice that there is a pickup tube here in the bottom. This bottle is designed for one-time use. There's a built-in valve right up here, check valve, which will not allow you to take and put anything in here once this bottle is empty. Typically, when you empty this bottle, you're going to recover the remaining contents out of this bottle, and you are going to recycle this bottle as scrap metal. There have been some people that have managed to figure out a way to defeat this valve and use these things, fill them up with air, stuff like that. I don't recommend it. Just remember, these bottles are designed for one-time use only. Once they are empty, you're supposed to take and render this cylinder unusable after the refrigerant's been pulled out, and then recycle as scrap metal. Here's an example which we saw earlier in the PowerPoint presentation. Basically, it shows how the refrigerant is going to flow depending on the position of the analog service gauge manifold set. In this case here, 134A is going to flow through here. If this valve is going to be open, it's going to go through the low side of the system. Notice here's the suction port. Notice that the service valve is in what they call a mid-seat or cracked position. So we have the ability to add refrigerant into this system. In this case here, this valve is also in a cracked position, and basically we can read the high side pressure, but this valve is not open, so we're not adding refrigerant on the high side. We are only adding it through the low side of this gauge manifold. Notice that the refrigerant cylinder is 114 psig, 95 degrees ambient around this thing, and notice that the pressure is less than 20 psig. So what we're trying to tell you is this: refrigerant should flow out of this bottle without any trouble into this unit. And by doing that, we are going to be able to charge the system. Where the problem comes up is when this pressure rises above the pressure in the bottle, then we have to overcome that by heating this bottle by utilizing warm water, not a torch. The idea is to increase the pressure temperature in order to overcome what's in the system. This is an example of taking 134A, putting it in a tray. The water is 90 degrees, a tub of warm water. The water should not exceed 90 degrees. We don't want water that is 115, 120. 90 should do the trick because it will overcome the low temperature, low pressure that is inside the bottle. And we should be able to take and push the contents out of this bottle by utilizing this concept. So typically, if we have a situation where the bottle is cold, we need to add refrigerant. We can utilize this concept of using a bucket with warm water and putting this refrigerant cylinder in there so that it will heat up and safely and push the contents of refrigerant out into the system. Okay, this is an example of gas will flow towards the cylinder if valve B is open. So now notice here we have the suction valve cracked, have the discharge valve cracked. These are your access ports for your refrigerant gauges. Here's 134A. So now what is happening here? Basically, refrigerant, if we take and do this, we're going to actually take and put refrigerant towards a bottle here, because the fact that the pressure here is higher than the pressure inside this 134A bottle. So you need to be aware of this. So if the pressure in the system is higher than the pressure in the cylinder, the refrigerant is going to flow the path of least resistance. And that being said, we need to avoid this, obviously. We always want to add refrigerant on the low side or in the liquid line whenever possible. If you try adding it through the high side, good luck, you're going to have a lot of problems. Okay, here we have a diagram basically showing how we are going to charge a system through the king valve or the liquid line solenoid valve here. Notice their bottle is inverted. We're going to take and put the liquid refrigerant through the gauge manifold set. And basically, we're going to go through the high side. But notice we're not going to be putting it in through the, we're not going to be putting liquid in the compressor. We're going to be putting liquid right here at the liquid line at the outlet side of the condenser, going towards the metering device. In this case, it's going to be a TXV. Please notice the position of the king valve or liquid line service valve. The valve is in the mid position. And of course, this is the gauge port. And that means we have access to the gauges at this point. And this is where the compressor receiver connection is made here. And then this is the refrigerant line connection. So in this particular situation, we have the ability to add liquid refrigerant because this valve is provided in the outlet side of the liquid line receiver. Typically, when I work on Amtrak rail passenger cars, this is provided so that I can take and add liquid, because we're typically talking about large amounts of refrigerant, anywhere from 25 to 50 pounds of refrigerant on average. Okay, this is an example of a charging chart for a 5-ton air conditioning unit. Basically, you're going to have the way you're going to plot this basically, and what you're going to do is you're going to record the suction line pressure at a given temperature. Okay, so you're going to look for the outdoor temperature. Okay, if it's 75 as an example, you're going to plot here, and then you are going to take the actual pressure that is being exerted on the low side of the refrigeration air conditioning system, and you're going to take and measure the suction line temperature. The idea is you want these lines to intersect, and if it doesn't intersect, that means you're either too low on refrigerant or you're too high. If you're too high, that means you have to remove refrigerant. And that happens a lot more times than you would be aware of. So is it possible to overcharge an air conditioned refrigeration system? Absolutely. Okay, here, this is a graduated cylinder. Notice that basically you have the liquid refrigerant here, 4 pounds, 4 ounces. And basically this is going to, you can utilize a cylinder like this in order to take and actually record the liquid level from the dial charge or the charging cylinder utilizing this method. The problem with the dial charge charging method is you have to create a situation where that refrigerant can flow. And the only way you can do that, at least the units that I used years ago, was we would have to vent off a portion of that refrigerant to the atmosphere in order for the refrigerant to go into the cylinder or to go into the system. That's one reason why I use scales, because they work just as well. This is a nice idea, but there are some issues with this. Okay, here's a chart showing the outdoor temperature, then it shows the evaporator entering air wet bulb. Why do we want to measure the wet bulb? It's very apparent. The wet bulb is basically the moisture content of the air. And of course, in basic refrigeration air conditioning theory, the way that you're going to measure the wet bulb, in the old days, we used a mercury thermometer with a wet sock provided. We would soak the wet sock at the base of the bulb where the bulb portion is located. And basically we would take this device and we would actually swing this thing in the surrounding airstream, and the water would evaporate on that mercury thermometer, and the actual result would be the wet bulb. Basically, it's measuring the amount of moisture that is in the air, okay? And a sling psychrometer is the name of that device I'm just talking about. We no longer use that type of device. We now utilize digital technology, and we still record the digital version of the wet bulb. The idea behind wet bulb is to make sure that we know the moisture content of the air. That's the actual real load of the evaporator coil. If we know the wet bulb, we're going to be able to take and make this and charge that system accurately. We are going to be able to determine if that system can pull out enough moisture from the air. Because remember, when you are doing the air conditioning process, not only you remove heat, you also remove the moisture content. Same thing holds true for refrigeration. So this chart is extremely important, and it'll tell you where we're at a given point. And by measuring the wet bulb, we're going to be able to determine if that unit is charged correctly. Okay, here we have a picture R134A, and then they give you the vapor and liquid. And I believe this picture is located in your textbook. And I believe you will find this, you will find this particular picture. Let's see here, 134A. I believe this is on page 267 of your textbook here. And basically what we're doing here is the temperature pressure relationship of 134. So V stands for vapor, L stands for liquid. And then you got the corresponding temperature and then the pressure per square inch. And then basically we can see what the liquid temperature is at 79 degrees in the condenser tube. So we can kind of determine if the system is properly charged and doing its job. Okay, this here is a, if I remember correctly, this is what they call a liquid charge faster type device. Let me see what your textbook has to say about it. I have something similar to this, which I never used. I purchased it for a train product years ago. And the idea behind it, it would actually meter, it would take the liquid refrigerant and cause it to flash off. This is on page 258 of your textbook under figure 10-9. This is a charging device in the gauge line between the liquid refrigerant and the cylinder and the suction line of the system. The device provides, well, basically what this thing is doing, it is taking liquid and converting it to a vapor. The idea behind it is speeds up the charging process. Liquid charging is always better. The problem is liquid charging through the low side can cause compressor damage. So if you have a device like this, basically it causes the liquid refrigerant to flash off before it gets in the low side of the system and hits the compressor, valve plate, whatever, and could possibly cause damage. Here's an example of a field piece scale. This is something that I have. Mine is the corded version. This is the wireless version. They work extremely well and they're accurate. They do a good job. The main thing you got to remember with these wireless units, you do have a distance, how far you can be away from the actual scale, from the transmitter receiver aspect of this system. Occasionally, these batteries have to be checked and changed as needed. You will get a battery message on the screen when it's time to do it. Please don't ignore it. Otherwise, those batteries will mess up this thing. All right, this is very important. These are refrigeration service access valves. Up in letter A, this is basically where the refrigerant connection basically comes in, and this is the device port where it leaves. And this is your service port right here where your gauge manifold hose, whether it be high side or low side. Then over here, you got a valve stem, which has a square end, and you have a packing gland. The packing gland in some units can be adjusted, but I'm going to urge caution on this. If you have a leak around this stem, which is not unusual, in some cases, not all, you can take and tighten this packing gland to take and stop the leak. There's also a cap that covers this valve stem when it's not in use. One of my favorite issues with a lot of service techs is they don't take and put the caps back on when they're done servicing the equipment. I have a problem with that. In letter A, take a look at the position of this service valve. The service port in this position is completely blocked. You have no access to read pressure, temperature to the gauge manifold. Now let's go to B. Now we have a situation where it's no longer blocked. We call this a crack position. By turning this a half a turn, quarter turn, now we have the ability to read the pressure temperatures of the refrigerant in this system. Now we go to the letter C. This is called the mid position of this section, the service valve. So basically the refrigerant is going to flow from here to here, plus we have access here. And then the letter D, this is front seating. When I say it's front seating, we're blocking off the flow of refrigerant here. So the refrigerant cannot flow through this valve. This is useful like on compressors. So let's say that you have to take a compressor out of a air conditioning system. If you front seat the valves, if they're equipped like this, then you can front seat them and remove that component with minimum amount of refrigerant escaping into the atmosphere. Works extremely well. Now, I would also urge some caution here. If you have a compressor that has these service valves, you need to still recover the amount of refrigerant that remains in the component to be removed. You can block off the lines, yes, that's true, but there's still going to be refrigerant inside the crankcase of the compressor and the immediate areas where the gauge manifold set is hooked up to this. Please be aware of that. Okay, chart based on 400 CFM per ton indoor airflow and 50% relative humidity. This particular chart is found on page 261. This is a charging curve used for charging a split air conditioning system that incorporates a capillary tube metering device. I can almost tell you with all certainty, if you're going to be working on air conditioning equipment, you're not going to run the capillary tubes too much anymore. They're obsolete. They do not do a very good job of controlling refrigerant superheat subcooling. They are an exact charge unit. The only time you're going to use a capillary tube is probably more on the refrigeration side of the fence. Air conditioning, the load varies. And because of the fact the load varies, it's a little bit harder to control the flow of refrigerant utilizing a capillary tube. However, if you have an old system that's a capillary tube, you may see a PT chart glued onto the service panel that looks like this. And it basically is going to tell you if you're in the parameters or outside of the parameters. And notice what we're utilizing as our determination if the unit is charged correctly is going to be refrigerant superheat. Okay, this chart here, this is back on, I believe this is on page 266. This is figure 1022. Basically, this is the temperature pressure relationship for R401 near the azeotropic refrigerant blend. 401 is made up of R22, 152A, and R124. At percentages of 53%, 13%, and 34%. Now, what I find very interesting about this illustration is if we have a leak, basically you don't know what you have left because these refrigerants are going to leak out at different rates. So what the concern is here, if you have a leak on a system where you installed a blended refrigerant such as 401A, basically you're going to have to recover what is left, find and fix the leak. After you've done that, then you're going to have to recharge this with new refrigerant because the refrigerant that is left is not going to be the same chemical composition as the refrigerant that was installed initially in the system. Please be aware of that. Okay, here we have a situation where we are adding liquid refrigerant. Notice that we are adding it through the high side of the system. This service valve gauge manifold set is open through the high side, but notice that it is attached right here. Notice that this valve is front seated. So we are putting liquid in the high side of the system and no liquid is going through the evaporator. In fact, this is probably going to be in a vacuum. Basically what's happening is we're filling up this liquid line receiver and we're liquid line and receiver. So the receiver is equipped with a sight glass. You're going to be able to fill this utilizing this procedure that you see in this illustration here. Typically, you're going to do this on large commercial systems, but you will not do this on small residential systems. Just be aware of that. And you're going to see more of this on the refrigeration side of the fence than you're going to see on air conditioning, although large air conditioning systems utilize a receiver. And the idea behind the receiver is to act as a storage tank for the entire refrigerant charge of that system. Here's that good old graduated charging cylinder. And notice liquid down here, vapor up here. When I got into the trade back in the early 70s, when I was still on active duty in the Navy, we utilized a graduated cylinder like this. The only thing I can tell you about this today is this is probably a museum piece. There's going to be a glass liquid column here. And this dial charge basically had the vapor, saturation, liquid temperatures printed on here, and you would literally rotate this plexiglass into the refrigerant, such as R12, R22, R502, etc. if we're dealing with small charges under 5 pounds. Typically, there's a 2.5 pound model and a 5 pound model. You will not be utilizing this in the field. And the reason why is when you add liquid here, in order to add liquid here, in order to fill a cylinder up, you have to open this up. So the only way you can open this up and make this work is you got to recover from this side. To me, that's a lot of work. Why not use a scale? This is a nice idea. And back in the day, it worked very well. But we are concerned about refrigerant emissions into the atmosphere. So this will no longer work in our current work environment. Okay, here we have an interesting situation here. The refrigerant cylinder will not drop in pressure any noticeable amount. And you notice that on the, looking at this system here, the gauge is fluctuating. Now, why is that gauge fluctuating? Why is that gauge fluctuating? That's a good question. We're looking at that, the gauge is fluctuating. And what's going on here? This is found on page 259. Manifold gauge is used to accomplish the same purpose. Basically, what we're doing here is we're accessing the system. We are utilizing liquid here, but notice that because the valves are front seated, high side, low side, we are not allowing any refrigerant to come in here. So basically, we're reading the pressure off the low side of the system. And this one here, we're not reading it. I'm assuming the reason is because the access valve is back-seated. Suction pressure at the low side service port, PSIG. Okay, this particular chart, I'm kind of curious to see where the book calls attention to this. Okay, this chart is on page 264 of your textbook, figure 10.20. This determines the desired suction line temperature based on the superheat and suction pressure. So you're going to refer to charts like this when you are charging refrigeration air conditioning systems to see if the system is has the proper amount of superheat or subcooling, depending on the application. Okay, here we have an interesting situation. You will see this a lot. Basically, this is on page 265. You got your data plate. It's going to show you the refrigerant that's in there. If it's a high efficiency, it's going to give you the full load amps, lock rotor amps, voltage 208 to 230, single phase, not three phase. And we want subcooling of 15 degrees. That's where we want to be. And the conditions that we want that to take place. And that's what's critical. If it's 95 degrees, the corresponding pressure should be 295 PSIG. At 115, which is our design point, should be at 390. Quite a big difference here, if you'll notice. Look at there. We're going from 95 to 115. And look what happens to the pressure just increases quite a bit here. So 295 to 390. So what we're doing here by looking at this diagram, we are determining if we have the right amount of subcooling and if this unit is properly charged or not. Design conditions for this particular, and you have to consult the manufacturer's diagram, 95 degrees going in. So we have 95 going in, we should have at least 10 degrees going out. And basically the liquid line temperature should be measured at 115 degrees with your field piece gauge manifold set. You just clamp onto the liquid line as well as to the suction line, and we're going to be able to determine instead of doing the math. But the idea is we want to get a 20-degree split. Notice that we have 75-degree air going in. We want to see a minimum 55 coming out. Last but not least, It's very important to record the current draw of the compressor. When the compressor is operating and if it's fully charged, we don't want to, this compressor should not be drawing excessive amps. It should be drawn close to the full load amp requirement in that compressor, okay? So current readings, very important. Clamp on amp meter, very, very important. But we want to take and monitor how much current this compressor is consuming when this system is properly charged. That will tell us if the system's operating correctly. We have some electrical issues that we need to deal with. And that is the end of this portion of the presentation.